Greetings all, and welcome to this evening's lecture. Today we're going to be covering what is termed Lecture 23 in the syllabus. This is for helical gears. Specifically, what we're covering is a portion of Chapter 7. Section 7.1 covers helical gears on parallel shafts. That's an important distinction, which we'll discuss in a little bit. Later sections in Chapter 7 cover worm gears and bevel gears. Those are done in separate lectures. So, helical gears on parallel shafts. Helical gears are very common in usage nowadays. Most, for instance, transmissions in automobiles use helical gears. And there's some reasons for doing that. They have a higher load carrying capacity than plain spur gears. They operate more smoothly, and they have lower noise. We'll talk about what factors power that shortly as well. But there are some very significant disadvantages to using helical gears. They are more costly. If you look at the picture of the helical gear, you can see that this tooth is angled, and that makes it a little bit more difficult to form. That difficulty in manufacture is why they are more costly. In addition, spur gears, at least in most circumstances, have a very low thrust load. That means that you only get a tangential force and a radial force with paired spur gears. Helical gears, on the other hand, create a thrust load. That means that you must have something to react against them in the axial direction, or they will move. So, let's talk a little bit about the nomenclature for helical gears. First off, there's nothing to panic about here. Most of this nomenclature is very familiar from spur gears. So I'm going to concentrate on the portions that are different. In this picture, we're looking at a helical gear edge on. The horizontal line here, the shaft, that is the axis that it is rotating about. So the first thing to know about helical gears is that they come in two hands, right-handed helical gears and left-handed helical gears. You can tell a right-handed helical gear from a left-handed helical gear by looking at it in this orientation. So we're looking at it edge on, and you can see in this case that the lines representing the teeth run down towards the left. This, therefore, is a left-handed helical gear. If the lines ran down on the opposite side towards the right, it would be a right-handed helical gear. The other important thing to note from this picture is the angle psi. That's the helix angle. It's the angle between the edge of the tooth and the axis of rotation. So as I mentioned, the nomenclature here is very similar between helical gears and spur gears. But helical gears do have that helix angle. There are several common values of the helix angle, including 15 degrees, 21.5 degrees, and 45 degrees. But you should note that there is no specific standard helical gear angle. Therefore, unlike spur gears, purchasing helical gears from separate manufacturers is difficult, bordering on almost impossible, because those helix angles are not standardized. Just like spur gears, helical gears do have a circular pitch. This is the definition very similar to spur gears, meaning the circular pitch is the sum of the tooth width and the space between teeth. Or, said another way, it's the angle along the pitch circle, along that arc, from a point on one tooth to the corresponding point on the other tooth, next tooth. But there's something a little different here. Because the teeth are angled on helical gears, we define both a transverse circular pitch. This is the same circular pitch you would have on a spur gear, and a normal circular pitch. The normal circular pitch means that we are going normal to the surface of the tooth. The normal and transverse circular pitches are related to one another by the cosine of the helix angle. You'll also note that for the normal circular pitch, we have a little superscript n. That's going to be the same with all of these helical properties where they're different, where we have both normal and transverse values. We will put an n in the superscript to denote the normal direction. Just like with spur gears, meshing helical gears must have the same circular pitch. Diametral pitch is, again, the same basic definition for helical gears as we have for spur gears. But there is, again, this normal diametral pitch, which can be related to the normal circular pitch and also related to the normal diametral pitch, or excuse me, the transverse diametral pitch via the helix angle. Again, if the gears have diametral pitch, they are imperial units, and meshing gears must have the same diametral pitch. Again, same with module. We have the same formula for helical gears that we have for spur gears. Again, there is a normal version of the module, which is related to the transverse module by the cosine of the helix angle. If we do have gears with a module, that means they are SI unit gears, and meshing gears have the same module. The diameter of the pitch circle is defined similarly to spur gears, but again, we need to be able to recognize whether we have the transverse circular pitch, if we're calculating the pitch circle diameter, or the normal circular pitch. The pressure angle of the helical gear is also tied into the helix angle, and because we can cut that section looking at the edge of the tooth either normal to the surface or transverse, meaning perpendicular to the axis, we can tie all of these angles together. If you play around a little bit with the numbers or look at a drawing, you should be able to convince yourself fairly easily that the transverse pressure angle is always larger than the normal pressure angle. Center distance is slightly different for helical gears. Again, I'll just leave you with the formulas and suggest to you that you run through sample problem 7.3. This is on page 474 of your book. One thing that we didn't really pay a whole lot of attention to in spur gears was the width of the gear. We only talked about that when we talked about calculating the tooth bending stress. However, with helical gears, face width is an important thing to bear in mind. This is the thickness of the gear measured parallel to the shaft axis. In general terms, the face width is restricted between 6 over the diametral pitch and 8 over the diametral pitch. But realize, that's only in general terms. This guideline is violated fairly regularly, depending on the application of the gears. When we look at the face width, we can also think about something called the axial pitch. The circular pitch is going in the direction of the pitch circle, so either normal to the surface or perpendicular to the axis of the gear. The axial pitch is measured along the axial direction of the gear. Continuing on, and this gets to the heart of why helical gears can be beneficial and why they're used in some applications like automotive transmissions. We looked at the concept of contact ratio for gears, and we discussed the fact that you always want to have more than one gear tooth in contact. The basic contact ratio formula that we looked at for spur gears also applies for helical gears. But helical gears have some additional contact, which is coming from the axial contact between the gears. There's more overlap between the gear teeth. The axial contact is equal to, defined by, the face width divided by P sub x. And when we look at the contact ratio for helical gears, we find that the contact ratio is equal to the contact ratio we would compute for equivalent spur gears plus the axial contact ratio. Therefore, helical gears of the same size have a greater contact ratio than spur gears. Velocity ratio for helical gears, though, is identical to the terminology and usage for spur gears. Now, let's talk about the other thing, the other little elephant in the room with helical gears, forces. We have looked at the resolution of forces on spur gears, and we find that the normal force on the tooth resolves down to a tangential force, which produces a torque around the axis of the gear, and a radial force, which always acts to try and push gears out of contact with one another. With helical gears, we also have, because of the angle of the tooth, an axial force. Let's take a brief look at a gear just to kind of get a feel for that. Here's a nice little spur gear. Rotate it around a little bit. You can very readily see that if we have a force operating on the surface of a tooth, we can resolve that, as we did in the previous video, into something that tries to make the gear spin and something that tries to push gears out of mesh. Let's look at the same size gear in helical shape. So, this is a helical gear, the same parameters as the spur gear we just looked at, but with a 45-degree helix angle. As you can see, if we have a force directly normal to this tooth surface, we will still get something that will resolve into a tangential force to spin the gear, something that will resolve into a force radially that tries to push the gear out of contact, but also, if you imagine this gear as something like a screw, a force that will try to move this gear along its axis of rotation. That is the thrust force. We can calculate this in terms of the normal force, the pressure angle, the normal pressure angle, and the helix angle. We can also relate these forces together looking at the transverse pressure angle. It's worth playing around with this a little bit, guys. Hopefully we'll get a chance to do a sample problem in class, but it is worth it to look at the forces as they resolve. Play around with your calculators a little bit. That's why you have them. The direction of thrust of the gears can be found by what's called either the right or left-hand rule. If you have a right-hand gear and your fingers are pointing, the fingers of your right hand are pointing in the direction of rotation, then the thumb of that right hand will point in the direction of the thrust load. Contrariwise, if you have a left-hand gear and your left-hand fingers are pointing in the direction of rotation, your left thumb will point in the direction of the thrust load. Regardless of this thrust load, the power transmitted by the gears is still the same. Power is equal to the torque multiplied by the speed in radians per second. There are a lot of ways out there that try to balance the thrust created by helical gears. A fairly common way is to do herringbone gears. Herringbone gears can take several different forms. As you can imagine, they're fairly difficult to make, but one way to do it would be to roll the herringbone pattern into the gear. Another way is to create two matching but different-handed helical gears and fasten them together, so we have a V pattern. With additive manufacturing, this becomes much easier, and you actually see herringbone gears very often additively manufactured, hence the fact that this gear is the one gear to rule them all and one gear to find them. Sorry, terribly geeky, I know. Now, we have so far only looked at helical gears on parallel shafts, but you can actually create crossed helical gears, meaning helical gears on shafts that are 90 degrees apart, or helical gears on shafts that are any angle apart. We do not cover this type of gear in the course, but it is covered in section 7.2 in your book, so if you're curious about it, I would say go ahead and take a look at the section. Crossed helical gears are a very interesting application. Finally, for reference, here are a couple of sources that you can click on to get some additional information, but your book also does a fine job of covering helical gears. That's all for tonight, and I will look forward to seeing you in our next in-class meeting.